All right. Hello, everyone. Thank you for coming for a talk on standing on the shoulders of giant de-obfuscating WebAssembly using LLVM. So we have a trade offer for you. You give us an obfuscated WebAssembly binary, and we give you a de-obfuscated one. But before that, a quick introduction about us. So myself, Vikas Gupta. I work as a senior security researcher at Thales, and previously I was working with Google as an Android security engineer. My interests are mostly reverse engineering and mobile security.
Yeah, hello everyone. My name is Peter Garver. I'm a principal software security engineer at Thales here in Singapore. Right now, I'm in the role of a product owner for mobile security group. So we mostly build mobile security components. And I'm the author previously of the Thales internal obfuscation tools, and of course, a passionate reverse engineer, but now mostly at the night. So why WebAssembly? So within of Thales, we build our components for different platforms like Android, iOS, Windows, Linux, you name it. But now we have requests also to move these applications into the web. So customers approach us and ask if they can use WebAssembly for those kind of transformation. Because, I mean, it allows you to easily transform all kind of source code and make it available for the web. So we thought, why not look into the security and to give them some kind of estimation that this is good enough for them.
And that's where our role as a pen tester, my role came in, that we want to evaluate the security of this whole experiment that we're going to do with the WebAssembly. So while starting, we had some of the questions that we wanted to answer. So as we said, one of the questions was, is WebAssembly secure enough for us? Then how do we go about the obfuscating WebAssembly? What is the tooling? How do we really approach it? How to lift Wasm to LLVM IR. We will be talking more about this in detail. And then finally, how to de-obfuscate the WebAssembly binaries. So we'll be talking and showing you some of the topics like how do we de-obfuscate how do we obfuscate and de-obfuscate using the existing tooling. We'll be introducing a new tool called Squanchy, which will be performing all the orchestration for the de-obfuscation that we're talking about. And then we will do some demos how the whole automated de-obfuscation can be done. So a quick introduction about WebAssembly. So it was announced in 2015, eventually launched in 2017. There was a need for some kind of a technology which can provide native level of performance for the web application. And you can think of WebAssembly like ARM or x86. So instead of compiling your source code to ARM or x86, you are compiling it to WebAssembly now. And instead of running on a hardware, which is ARM or x86 compliant, you are running in a virtual machine. So there is this virtual runtime, which will be taking care of executing the WebAssembly. And this virtual machine is stack-based. There is a wide adoption of WebAssembly as of now. So a lot of games are using it. A lot of big web applications are using it, like Google Earth, blockchain applications as well. So there's a wide adoption of WebAssembly now. Now, WebAssembly binary, you can call it as a module, and each module is divided into sections, and each section contains all the information which is required to execute a binary. So for example, you want to know the exports, the imports, the functions, the memory. So all this information is encapsulated into these sections. And the good thing is that all this information is indexed. So what does it mean? For example, if you want to execute a function, you should know the index of that function. You go at that index and you execute it. Similarly, for the memory as well, it's like a flat array, and you just go at the indices to access that part of the memory. So you will see that never the real addresses are exposed to the code which is executing, and it is kind of a security feature of WebAssembly. Another thing you will note that there is no indirect jumps. So what does it mean? So WebAssembly won't be using structures or instructions like gotos. So everything is structured, everything is neat and clean. You can see the whole control flow in once. In terms of tooling, we have two good projects. One is the binary toolkit and the other is the Wasm tools. It provides you most of the tooling which is required while you're dealing with WebAssembly. Some of them we have mentioned over here, like we are using Wasm to C and Wasm mutate a lot, and we will be showing you in the later on in the presentation as well. And in terms of GUI-based decompilers, so we have Ghidra. You can use a Wasm plugin, and yeah, you can decompile the Wasm code using Ghidra. If you look at the other tooling like IDA Pro, JEP Pro, they're kind of hit and miss with WebAssembly. So sometime it works, sometime it doesn't. So we are mostly using IDA Pro for looking at the native code, which we may generate during the de-obfuscation process. So a quick introduction about obfuscation. So obfuscation is the process or a technique where we are trying to make it harder to read or understand the code. But we want to preserve the original behavior of the code at the same time. Often we hear about obfuscation in context of malwares, that they use it to make the analysis harder. But there are a lot of legitimate use of obfuscation as well. So for example, if you're delivering an application to an end customer and want to ensure that the IP is safe, you want to obfuscate the application. Similarly, if you're dealing with media, the DRMs, which are there on the devices, they use obfuscation as well. In context of WebAssembly, we can apply obfuscation at different levels. So let's say you start with the C source code, and now you want to perform obfuscation. So let's say you want to perform right at the C source code level. We have a tool called Tigress, which operates at the source code. You can perform obfuscation over there. If you have at the IR level, you have compiled the C source code to the LLVM IR, then you can use the tool like OLLVM. And let's say you are at the Wasm level itself, you have the binary, you can apply tools like Wasm mutate. It's kind of a pseudo obfuscation, it's a diversifier, but it does the job. Over here, we will be using a lot more of LLVM-based obfuscation. And if you see, we are applying the obfuscation using tools like OLLVM, Hikari, Polaris. All these are open source, available on GitHub. And you can apply these tools on the middle end of the LLVM compiler chain. The good thing with this approach is that it is kind of language agnostic. So you can start with any language like C, C++, Go, Rust, it will work for them. So OLLVM kind of started this whole revolution of using LLVM for obfuscation, and it had some very basic introductory passes, I would say. So 4 of them are here, like substitution, flattening. Slowly, this thing evolved. Now we have tools like Hikari, which is performing indirect branching as well. Some extra transformations are there. And if you look at Polaris, which is kind of the most maintained one these days, it has a transformation, a new transformation like using of linear MBAs. So give you a taste of how obfuscation looks like. So over here, we have a case. Right on the top left, we have a simple example, a simple instruction, a simple expression. And if we apply the obfuscation on this one, so you see at the bottom left, that it kind of expands. It becomes slightly complex. But if I apply this obfuscation multiple times, so now I'm applying 3 loops of it, and the one you see on the right is the same expression but blown out. So you can see that's, yeah, it is not that human comprehensible anymore. And now we apply the same thing with the control flow. So now you have on the left-hand side a simple input, but I apply 1 pass of obfuscation, you will see that the control flow graph is increasing. And if I apply it 3 times, you can see it's massive now. So more the obfuscation we apply, we can see that the code size is increasing. So in our case, like we started with a simple code, and in one of the cases, we saw that the size became of 12 megabytes. And in many cases, we see that the tools start breaking. So Ghidra is not able to decompile it. We are reaching the limits what Ghidra can handle.
So let's talk about de-obfuscation. So with de-obfuscation, we try to reverse the process of obfuscation, right? We first try to make it hard to understand what's going on. And in de-obfuscation, we try to simplify it to make it readable again. So we try to revert all those kind of transformations that Vikas was showing. In classical obfuscation, we were mostly talking about pattern-based obfuscation. So the tools have introduced simplification or obfuscation patterns. They were looking for assembly code to replace. And then one by one, they were introducing those patterns to make it hard to understand. There were also constant unfolding or junk code insertion to trick either Pro or Ghidra to make it difficult to read the code. And in classical de-obfuscation, we were building tools based on simplification patterns. So we try to identify those obfuscation patterns, build tools that were searching for them, and then replace them one by one. But unfortunately, the things have changed. Now we have powerful technologies like compiler-based obfuscations, so we needed to adapt. So we tried to tackle the problem of obfuscation now with several intermediate languages that, like you will see in Binary Ninja, right? You have all those kind of languages that allow you to modify the code. And we now try to be more generic. We try to introduce generic optimization patterns that help us to process the process of obfuscation and simplify the code. So in 2019, Matteo Favaro and I introduced a paper called Saturn, software de-obfuscation based on LLVM. And what we showed is that we can tackle the problem of obfuscation by using compiler technologies. So we have a generic approach of de-obfuscation based on LLVM compiler optimizations. And in most cases, we were able to show that we can weaken the obfuscation and in best case, even completely remove it. So what was the approach, or what is the approach of Saturn? So you take the input binary like macro, ELF or PE, then we use one of the lifters like weml from trail of bits to lift it into LLVM IR. Then we're going to apply all kind of optimizations. We also have some custom passes to detect the upper predicates. So once we simplify the code, we're going to brighten it. Brightening means that we want to make it more readable. So if you're going to further reverse engineer or analyze it, you want to have some readable code. Then we use one of the backends to emit the object, and either we patch it back into the input binary, so you can still debug the binary, which is quite comfortable, or you just emit the patch file and you're going for static analysis in either or, whatever you like.
Now, the idea that was introduced is that we can use compiler for de-obfuscation. So we started with a tool called Binarian. It takes WebAssembly as the input and WebAssembly as the output, and it performs some optimizations in the middle. So we thought, in theory, it can solve a problem. We gave very simple obfuscated program as the input, and it was not able to de-obfuscate it. So it kind of didn't work for us. We need to do some thinking. And then we went back to the idea that, okay, let's lift it to LLVM IR, and let's see how it goes from there.
So why LLVM? LLVM is a target-independent optimizer and code generator. It is based on the LLVM IR, which is a language-independent and quite feature-rich. And the advantages are it's a world-class optimization analysis passes. So the best engineers in the world, from Google, Apple, you name it, work on this compiler to develop compilers for like AI or ROCm, NVIDIA. Basically, it's used everywhere these days. This feature-rich intermediate language, it has a nice accessible API to modify the LLVM IR or the control flow graph. And after optimization, you can see the code as normalized because all those passes generate basically always the same code. So it's quite useful if we want to do some pattern matching afterwards. And it has all the several backends for recompilation. So once you're under LLVM IR, you can always go back to native to execute the code. And it's fast. Because in obfuscation, we deal with heavy obfuscated large functions. So we need tools that can handle it. And LLVM is made for it. So what are
But there are challenges while lifting the code. So we are taking from one language to the other one. So one of the most important thing is the correctness. So whatever the original logic is, it should be reflected in the lifted one. Then you should be able to capture the side effects if there are any in that original language. And we will see in case of WebAssembly that we want to capture the information, the runtime information as well. This is very important in case of WebAssembly to perform the proper de-obfuscation.
So what are the lifting principles? On the left, you see some simple Wasm assembly code sample and with some simple instructions. So when we want to lift it, we of course need to first look at the semantics and the implementation of the specification. So here we can see the opcodes don't have any side effects, so which is quite useful because compared to x86 or ARM64, you would need to take care of all those side effects. But WebAssembly is quite simple. It just really does what it has to. And on the right, we can see the lifted code. So at the beginning, it looks a little bit bloated, but the semantics are correct, and the function performs the same as the one on the left.
So now our goal was, can we find a tool, existing tool, which can lift the WebAssembly to LLVM IR? Now, there is this runtime called WebAssembly micro runtime. It has a subtool called WAMA compiler. Now, this compiler has one of the features to emit the LLVM IR, and we thought, why not? Let's start with this. But once we start using it, of course, it was able to handle some basic scenarios, but soon we realized it doesn't work for the complex examples. For example, uh, all the debug information or the symbol information is lost. So you are seeing over here that the functions are renamed to AOT function 1, 0, 10, and so on. But most importantly, all the environment, the runtime environment information, so all the globals, the tables, all that information was lost. And as we said, this information is important for us. So overall, this idea didn't work. More thinking needs to be done. And yeah, we need to figure out how to go.
So we took a look at all those kind of lifters available that can handle WebAssembly. So as Vikas mentioned, binarian that didn't work for us. It also relies on the binarian IR, which is a custom IR. And of course, we don't want to write our own custom passes for this IR. So yeah, we skipped it, and the code was not folding. WebAssembly, as Vikas explained, lifted to LLVM IR already, but it was missing all those kind of features that we will need to make the code fold further, like the handling of globals and functions. All this information was just missing, so not a good candidate for us. And then we came across about Wasm2.js. So here it lives into JavaScript. So at the beginning, it might look like it's not a good candidate. But if you looked at the JavaScript code, it was pretty clean. And it looks similar like pseudo C code. So you added some brackets, a semicolon, some gotos, and you could easily compile it, which was quite useful. And the code was already starting to fold. So we thought it's a good candidate. So I started to implement all those missing features because it was also not able to handle function, the index function that Vikas was mentioned, the global. And after a week, I discovered, oh, I'm basically re-implementing what Wasm2C has already implemented. So I continued with Wasm2C, and this looks like the perfect candidate because it lives into C code, and C can be compiled into LLVM IR. It has this instance parameter, which was a little bit annoying in the beginning, but we will explain later why it's very useful for the obfuscation. And at the beginning, the code was not really folding, but still we thought it's a good candidate. So what is our lifting idea? So we start with the Wasm binary. We're using Wasm2C to lift it into C source code. Then we're going to use Clang with O0 optimization, which means no optimization, and emit the LLVM IR. Why O0? Because recently LLVM has introduced the concept of opaque pointers. And opaque pointers means that we might lose type information about the data we're accessing. But we need at least type information in the beginnings to make the code fold better than it would without the types. So once we are in the LLVM IR, we can use optimizations to fold the code. We can inject a runtime because now to the API is quite easy. And once we are done with that, we can use either the backend to compile it into the native object and continue the analysis with either Pro or other tools, or we directly compile it back into the Wasm object and just execute it as before. So what is Wasm2C? Wasm2C is a great tool to lift WebAssembly into C. This is well-defined Wasm runtime that helps us during de-obfuscation. It has all those helpers that initialize the runtime. Usually when you want to execute the WebAssembly, you need to initialize everything in memory. And we have those helpers already in code. They are generated by Wasm2C. It also comes with helpers for the globals, and it has some helpers for load and stores. So you won't see load and stores directly applied in the code, but it's always through a function that does the operation. And most importantly, it doesn't modify the original control flow graph in the beginning. So it means after obfuscation, we retrieve the same control flow graph when we're going to lift it, which is quite useful if we want to go for the obfuscation. There are some shortcomings. At the beginning, it's not able to access the tables, but we can show you how we can achieve that. So here's a motivating example. We have a simple add function. So at the beginning, we see a loop over an array. That's going to calculate a constant. Then we see an if statement, which is basically an opaque predicate. And if this opaque predicate is true, it's going to add 1911 as a constant. Otherwise, it's adding another constant. And at the end, it's going to summarize everything together. So this can be seen already as an obfuscated function because usually you don't write such code and you need to spend some time to understand it. But if our approach works, we basically end up with the code on the right, which is just one simple statement. So let's apply our concept with Wasm2C. So on the left, you see a more simplified version to make it a little bit easier. We're going to apply Wasm2C to lift the code into C. You can see we have the nice and lifted functions. Now we're going to apply the O3 optimizations from LLVM. The code is nicely folded. We can already make it more readable. And at the end, we use Clang to optimize into the binary, use either Pro and Hextrace to decompile it. And we can see, oh, we achieved our result.
So we mentioned about this instance parameter. So when you're lifting with Wasm to C, so the C code will contain this W2C instance parameter, which is passed to all the functions. Now, this parameter is quite important because it encapsulates all the information about the runtime. So we are talking about the memory structures, the function tables, the globals, and all the information is kind of encapsulated in this one variable. The other good thing with this particular variable is that all the initialization of this information is also taken care by this by Wasm to see. So as we said, a lot of things that we wanted to see is taken care by Wasm to see related to the runtime.
So yeah, what is our deobfuscation idea now? So as a lifter, we're going to use Wasm to C to lift the code into the LLVM IR. Now we introduce our new tool called Squanchy. So Squanchy is taking care of all the orchestration. So interact with third-party tools like Simba++, CLI, or Super. It applies optimization, injects the runtime, takes care of the helpers, and basically orchestrates it to all the process. Once it's done, it's going to emit the LLVM IR. Now we can take one of the backends and compile it into native, and then, as said before, we can use one of the tools to analyze it. So what is Squanchy? Squanchy is a tool to automate several obfuscation steps. It does the orchestration of third-party tools like SimLLVM or Simba++. It's there to model and inject the runtime into the function you would like to deobfuscate. It inlines all the dependencies accordingly into the function that we want to deobfuscate again. And it optimizes the function and model. Here we also have a customized pipeline that preserves the control flow graph at the beginning, so we can do better analysis, at least at the start. And then when it's done, it's going to remove all the Wasm to C runtime that was injected, when you lift the code, and you get a nice and clean function at the end. So this project will be available, or it's open source after the conference. So yeah, let me go here.
Yeah.
So as Vikas explained, we have the Wasm to C runtime initialize functions, and we're going to make use of it to start the deobfuscation process. Because as Vikas mentioned at the beginning, all the memory access is going through indexed memories. So when we try to deobfuscate, it will not work at the beginning because the information is missing for the optimizer. So we need to make it available. And that's where we use the runtime initializer generated by Wasm to C. It has initializations for imports, global tables, and it relies on other Wasm to C helpers and some helpers that we provide in Squanchy that do the low-level stuff like allocate the memory, function references, and the load and stores. So we're first going to allocate a local Wasm to C instance. Basically, it's the same that usually will be provided by the function as the first argument, but we allocate it locally at the beginning of the function, and we place all the references of the first parameter to it. Then we're going to create a new call to the Wasm to C runtime initializer that Vikas was showing. Because the code is already there, we don't need to implement it on our own. We just need to create a call to it. And the argument is our locally allocated Wasm to C instance. Then we're going to mark all the functions inside the Wasm to C runtime initializer, and Squanchy helpers as always inline. LLVM has this mechanism to help you inlining with the code. So why not make use of it? Now we're going to inline recursively. We start with the dependencies that are in the Wasm to C functions. Of course, this first call to the initializer. So we're going to inline the functions accordingly into our function to make the information available for the optimizer. Then we continue recursively until no functions found that needed to be inline. Now we're going to apply our O3 pipeline and preserve the control flow in the beginning. So yeah, why do we need to preserve the control flow graph at the beginning? So obfuscation pipelines are not randomly applied. If you would do this, the code will just grow maybe too big, so you can't really use it, your customers would complain, or the performance would be too bad. So you need to think about some pipeline to take those things into account. And what we usually do, you have the strategy to first apply like control flow protections. So here we can use control flow flattening. Then we're going to protect the code. Here we can use instruction substitutions. And then, of course, we would like to harden their protection. So we use opaque predicates or mixed Boolean arithmetics to make it more difficult to deobfuscate the functions. But for de-obfuscation, we would like to reverse the process, right? So we keep the control flow in the beginning, and then we start from the back one by one.
Okay, so with any engineering software, you make trade-offs, and that is what LLVM is doing as well. So LLVM is doing a trade-off between how much to optimize and how much time to take. You can spend more time on compiling it, getting the most optimized code, but then you want to do it in a reasonable time as well. And these kind of are defined with the threshold. So these are these variables where you can define how much trade-off to do. Over here, we have two examples, one with the loop unrolling and other is the dead store elimination. So take an example that you have this huge function, which is using a load right at the top and store at the bottom, or the other way around. And if you have these optimization levels low, or the thresholds are lower, then LLVM may not go right at the bottom to optimize out few things. But if we say that do your best, take all your time and do the optimization, then LLVM will do it. And that's what we are giving hint over here.
Okay, so once we're done with the optimization process, we need to start the brightening step. So in the brightening step, we would like to clean out all the things that are left from Wasm2C and make it more readable, right? So we, again, replace the local Wasm2C instance with the parameter again, because there might be calls that still depend on it. So, and we want to make it functional, so we need to provide this parameter to those calls. And we're going to clean the leftover initialization code from Wasm2C. So we end up with a nice and clean Wasm2C de-obfuscated function. So now we can use one of the backends, or at the beginning we can stay at the LLVM IR, and then here you can see an example from the generated ARM64 code.
Okay, so now we have all the information about lifting, how the things will work. Let's apply it for de-obfuscation. So a reminder, this is a simple input that we are taking. All we need to care over here is that there are 4 expressions that we care about, like just 4 expressions. So this is a case where we have applied instruction substitution 3 times on one of the expressions, which is on the left-hand side. And on the right-hand side, you can see that the expression number 2 is reduced a lot, and the other expressions are recovered as well. So this is just to emphasize that LLVM do work, and in some cases, it has broken it completely, and in the other cases, it has weakened it a bit. So we have one tooling in a pipeline now. But LLVM have some shortcomings. For example, it cannot handle the cases where control for obfuscation is there, or let's say you're using a lot of complex MBAs. LLVM cannot handle such kind of a situation. So we need some kind of a tooling for this. Let's talk about MBAs. So MBAs are these expressions which use a mixture of arithmetic expression and the Boolean expressions. So for example, plus, minus, multiplication used with and or. And it creates a kind of a combination which is hard to figure out or hard to solve because there are no simple rules like distributivity, associativity. There are no such rules of interaction with MBAs. SMT solvers can solve these kind of problems, but once they become too complex, yeah, they kind of break. So we have some specialized tool in the recent times called Simba and Gamba, which specialize in breaking the MBAs. And then we have a tool called Simba++.
Yeah, so Simba++ is a tool that helps you to detect those kind of MBAs in the LLVM IR, because it's a problem for itself. I mean, where do those MBAs start? Where do they end? What are real expressions? What are MBAs? So it's not that easy to find them. But Simba++ helps you here. So it identifies those expressions, tries to simplify them with one of the algorithms like Simba, Gamba, or you can use an external solver also for that. And then it's trying to prove that the simplification is right by using SMT solvers. Once it's proven that the expression is right, it's going to replace the MBA with a simplification in the LLVM IR code, so we can de-obfuscate them.
Let's apply it. So now again, we have one expression which is obfuscated on the left-hand side. So this is just one expression. When we apply LLVM optimization, we can see that it is reduced a bit. Then we apply Simba, it is further reduced. And when we apply Gamba, it is like quite manageable now. So you can see that each of the tools have their own advantages and they do reduce an expression a bit. Now the challenge related to control flow obfuscation still remains, so we need to find a solution for that. So we came across this paper called Super. Super is a super optimizer. and which means that it is kind of finding optimization which the compilers generally miss. So it is doing some additional optimizations. It is using some advanced algorithms like synthesis, data flow analysis to perform these optimization. And it turned out to be a perfect candidate to de-obfuscate control flow obfuscation. So in this example, we have opaque predicates, and of course, we have applied control flow obfuscation. So on the extreme right, you can see like this whole big graph. And when we apply super, we can see that we are able to recover the original 4 expressions we talked about. So it does work, and we should take a moment to thank super. So now we have all the tooling which is required to handle the various cases. So let's apply on a complex example. So over here, we applied all the various transformations on this obfuscation. So we get a big complex code, which is containing all MBAs, control flow obfuscation. And you will see that we were able to recover the 3 expressions completely in the original form. And one of the expressions was weakened, but I would say it's still manageable. So now we have set up the whole base that our approach works. We have tested on the POCs, but let's apply in the real world. So we started looking around. We found that, yeah, WebAssembly malwares are increasing, and predominantly these malwares are being used for Bitcoin mining through your web browsers. Then we came across this paper where they suggest that you can use Wasm mutate to diversify these malwares. So what it means is that, let's say you have some signatures for your malwares, but now you apply Wasm mutate, a few iterations of it, and it is diversified. So it's kind of a new binary. And when these authors submitted these new binaries to VirusTotal, these malwares were not detected. So they behave like a new malware if you think about it. So it's a good idea if we can target Wasm mutate. If our approach can solve it, then we can handle a problem of malwares as well.
Oh, yep, demo time. So what we will show you, we will apply Wasm mutate on a simple example. Here we will use 3000 real iterations. Real iterations means that some of the passes in Wasm mutate are broken, so we need to detect them. And we do it 3000 times, which is almost, yeah, we hit the limit of the function size of WebAssembly. And we will show you that we can remove 100% of the mutations. So the code is normalized, as we introduced in the beginning. So it means, as Vika said, if you would like to use signatures, you can build your signatures on top of that, because now the code is normalized. And even if the samples are obfuscated, it should still match, right? So let's see here. Okay, run demo. So it's first going to protect the sample. Now we're going to open it in IDA. Let's see for the protected function. Take some time because it's big. Okay, you can see that. Okay, so let me fit it. And as you can see, we generated this really huge function. It's, I think, around, yeah, 60,000 K of kilobytes. Yeah, and now when I close the screen, it starts the de-obfuscation. So you can see the performance of LLVM live, and we're done. It's funny because it really performs that fast. And we can see our de-obfuscation approach has worked, and we reached the original expression again. Okay. Maybe some numbers. So we started with 200 instructions, and after the first optimization step, it's already simplified to 20 instructions. Then we're going to clean up the Wasm to C runtime and so on. We end up with 23 at the end. So it's quite successful. Yeah. Okay. Yeah. Then we came across. Thank you. Then we came across. Then we started to look at what's there in the wild. So we came across a Bitcoin miner called Kryptonite. So when you open the web page, the WebAssembly code will be loaded and the code executed, and it starts mining Bitcoins on your PC. And then we find also an obfuscated version of the Kryptonite code. So we were interested, are we able to de-obfuscate the functions, and will they match the original code? So we selected some of the functions, and yeah, our approach works. We saw that the code matches 100% the original one. In one case, it didn't. It had some more code than we initially saw in the original sample. But after looking into it a bit deeper, we saw that the obfuscated sample inlined some of the code into the function. And of course, and then when we compared it with the inline code, it matched. So it completely works.
Yeah, we also saw that edge captcha is using WebAssembly and the code is obfuscated. So we thought, why not let's apply our approach to de-obfuscate it. We applied our approach on some small and medium-sized functions. So what you're seeing over here on the left-hand side is a function which is using control flattening obfuscation. And on the right-hand side, you see the de-obfuscated one. And it looks a slightly bigger because some of the information is inline now. But once you decompile it, you will see that the code is very much readable. Okay. Time for conclusion. So we demonstrated to you that how we can do obfuscation using the existing tooling based on LLVM IR. So we have OLLVM, Polaris, Hikari. So we can use all these tools for Wasm obfuscation. We showed you that we have Squanchy, which can perform all the orchestration for de-obfuscation. So taking care of the shortcomings of lifting Wasm to C, including the runtime information, all the thing can be handled with Squanchy. Then we showed you various tools that we came across that we can use for de-obfuscation, Simba++, Super. We applied all this knowledge that we gained on the real world applications. For example, with the malwares, we saw some commercial products as well. So it works. And last comment, I would say that in the academia and around, if you see, there is a lot of work going on that they want to create a new tooling for WebAssembly. And in our experience, we will say that the existing tooling is sufficient. Also because it is battle hardened, there are less number of bugs, well used. So we don't need to rely on the new tools. And instead, if there is a special requirement, you can use the existing tooling or improve it. With that, thank you.
Yeah, thank you, everyone.